The talk is about stratigraphy, which is one of the subfields in geology. It deals with sedimentary rocks. I'm going to talk about how it affects our lives. But first, I'd like to congratulate our chief scientist, Spock, aka Pete Morrison. Seriously, he's done a hell of a job getting this program going, and we thank him for his efforts. Also like to thank Marty Miller, sitting in the back there on her phone. She helped put together this PowerPoint presentation, and which I would have been lost without her. And of course, Phyllis and Karen have helped to make this thing happen also. Onward and hopefully upward. These are beds of limestone, and each bed is a stratum. You can see that it dips toward the road. Not sure if the road is tilted somewhat or the beds are tilted severely, but these are limestone beds in Cyprus, of all places. We might as well start at the beginning, and I see we have a seat, Maria. Beginning is the Earth's formation. Earth was formed 4.6 billion years ago, quite a long time. And back in the beginning, there were only igneous rocks because the Earth was very, very hot and quite molten. And eventually it started to cool, and igneous rocks were formed from the molten mass. I've seen different numbers on this, but a number I saw was it took 1 billion years for rain to start to fall on Earth because of the extremely high temperatures and the fact that all kinds of chemical reactions were going on, and finally water was formed and it started to rain. Once it started to rain, it started to weather the igneous rocks into its component parts. Igneous rocks are composed of quartz and a whole bunch of other minerals, some of which, when they weather, produce clay minerals, some of which produce some calcium carbonate, and some salts. And eventually, these are deposited in the oceans that it formed. Quartz is the main component of most of the sandy beaches that we see around the world, although there are some calcium carbonate beaches around the coral reef islands in the Pacific. And there are a few salt beaches on areas where, like around the Dead Sea and places like that, where we're getting a lot of evaporation. Here's another picture of a series of strata of sedimentary rocks, starting with probably silt stones. Silt stones are essentially fine-grained sands with some clay, and going in and out of shales and probably limestone here and back into sandstones and siltstones. The depositional environment for the formation of these sedimentary rocks, predominantly oceanic, but it depends upon the depth of the ocean and the currents. Many of the deposits that I'll talk about were formed in environments where the waters were flowing rapidly, like along beaches, river deltas, and actually rivers themselves. Of course, you see things like coals and dark shales. They were deposited in either swampy areas or perhaps large lakes where there was very little water flow, and these organic materials were deposited. We have to go back to about the 1600s to find out that people who are actually starting to study the stratigraphy and the formation of these rocks that were sticking out all over the place. And there was a fellow named Nicholas Steno, a Danish philosopher, theologian, and part-time scientist, who started to look at the beds of rock and came up with a theory called the law of superposition. The law of superposition really just states that the oldest rocks are at the bottom and the younger rocks are on top. This is pretty obvious to us now. It wasn't so obvious to people in the late Middle Ages and early Renaissance periods. A couple hundred years after Steno, a gentleman named William Smith, who was a British fellow, got involved in the study of the rocks of Great Britain, and he started mapping the British Isles and found that you could correlate the rocks from one location to another. And so that started the science of stratigraphy. You could realize you could correlate over rather long distances, but some beds are straighter in the British Isles. And in fact, we'll get to this a little later, but many of the geologic periods have British names because they were mapped first in Britain and named by British geologists. What happens to the minerals as they fall down to the bottom of an ocean or a lake? They turn into rocks. Lithification is the formation of rocks. And the rocks are created to increase in hardness because of the depth of burial. The pressure of the overlying sediments squeeze out the water and also reorient some of the mineral grains so that the rocks are harder than just the unconsolidated muds that we see on the surface around here. Cementation is when solutions are migrating through the pores of the rocks. Some of them move very slowly in the fine-grained rocks like shales, and shales are composed of clay minerals, and they're very fine-grained, and the movement of water and solutions of cementation materials very slow. Sandstones can move much more rapidly. And the cementing material can be calcium carbonate, I talked about before, can be iron solutions that you'll see some sandstones are very reddish. These are deposits of iron minerals around the coarse grains, creating a harder rock. And then with the depth of burial, you get increasing heat, and some of these rocks become very, very hot, and that heat causes some melting of the minerals and additional cementation. There's a type of rock that is called a metamorphic rock that are sedimentary rocks that have undergone really high heats and intense pressure, and these do not particularly resemble sedimentary rocks anymore, although they can see some stratification. They resemble granites, more closely granites and other igneous rocks, although some of these things are kind of halfway between. There's a famous rock, and I don't know how many New Yorkers are in this audience, but there's something called Manhattan schist. Schist is a metamorphosed shale, clay rock, and it's the bedrock that most of New York is built on. I won't get into structural geology now. We'll talk about some geologic structures when we get to talking a little later in the discussion. Correlation of these strata across distances can be either with just looking at the rock type and studying the mineralogy of the rock, can be looking at fossils or biostratigraphy, can be chemistry. You look at the actual chemical composition of the rocks across long distances, and there may be trace elements that are very persistent across long distances. I was actually watching a show last night about the death of the dinosaurs, the end of the period where dinosaurs ruled the earth, and talked about the fact that this huge meteorite hit just along the north edge of the Yucatan Peninsula and created this tremendous cloud that went all the way around the earth and changed the climate and everything else and caused the death of the dinosaurs. And there's a very thin layer, only a few millimeters thick, of iridium-rich material around that marks the end of the period of the dinosaurs. And so this is a trace element that can be traced across enormous distances. And then there's chronostratigraphy, where people look at the age of these rocks. And of course, that's a combination really of looking at fossils, looking at their position in the geologic column, and a little bit of mystery going on there. Periods, groups, and formations. Periods are, oh, I hit the wrong button. Well, here's a good example of what they call a cross-bedded sandstone. The individual strata are marked by these thin red beds, but in between you can see these striations. These are sands that were deposited in a very rapidly flowing water environment, probably a river or a series of rivers wandering across the delta. And these are very prominent. This is something called the Navajo sandstone. It's very common exposures in New Mexico, Utah, that Four Corner area of Arizona and Colorado. I talked about periods and formations. This is a cartoon of geologic history. And this shows that at the very base of this thing, the Earth's forming at 4.6 billion years ago. And each of these large groupings here are called eons, and then there are these eons down below. And each of these thin beds, which constitute down in the lower portion many millions of years. For instance, this is 60 million years. That's the length of time of the Cambrian. And the Permian was around 45 million. And then we go to the modern days, the more modern era after the extinction of the dinosaurs. And this shows only 65 million years, only 65 million years. To geologists, 65 million years isn't a long time. We tend to think in somewhat longer periods of time. But this shows also, and this is in your handout, that there's a tremendously large extinction at the end of the Permian period. Permian, by the way, is the name of the very prominent oil basin in West Texas that is producing a lot of our oil through fracking these days. So the Permian Basin has Permian rocks in it, needless to say. Then, of course, at the end of the Cretaceous period, had the big extinction of the dinosaurs. And that's when it's theorized that this huge meteorite hit the Earth and caused the extinction. This meteorite was thought to be a couple miles across. Doesn't sound all that huge, but when they're traveling at speeds of 25 to 30,000 miles per hour, the impact is enormous. And it hit right on the edge of the Yucatan Peninsula, and it particularly showed, the Nova showed that it drilled down through the center of this crater and the tremendous distortion of the bedrock caused by this impact of this meteorite. And then, of course, we get to the era of the mammals, the so-called Cenozoic era, where we start out with mammals that are very small. They find fossils of sort of proto-animals in the Jurassic and Cretaceous area. They were very small, they were not much bigger than raccoons at the largest. And then all of a sudden, within a few tens of million years in the Paleocene, you had these gigantic animals. They many of them grew bigger than elephants, modern day elephants. And there was an interesting theory purported in this discussion, in that we have descendants of the dinosaurs, not only in crocodiles and other large lizards, but the theory is that these winged lizards eventually evolved into all of our birds. And let's face it, birds are different than most mammals in that they lay eggs and are not have the typical equipment that most other mammals have.
How many of those layers would the Grand Canyon show you?
Well, Grand Canyon starts all the way back in the,
But can you see it? I mean,
you can go down to see Precambrian rocks. In the
really?
Grand Canyon, yeah. Yeah. Oh, yeah. And if you look at, I didn't bring a geologic map of the United States, or rather North America, but there's an area in Canada called Canadian Shield. That's all Precambrian rocks. Much of Greenland is dominated by Precambrian rocks. There are, by the way, some fossils found in this Proterozoic. The Proterozoic is a name of protozoans. They are very small, single-celled animals. Well, there are some deposits found mainly in Australia called stromatophytes that are thought to be accumulations of these beasts that were in colonies and formed these mounds. And I have a little picture that shows a whole bunch of these mounds across a fairly large area. Fairly large, I mean, a few acres. Well, stratigraphy is not just an academic science. It affects us. And now we get many of our really important minerals from sedimentary rocks. And these are petroleum and natural gas, wholly produced from sedimentary rocks. Coal, lignite, bituminous coal, lignite, bituminous, and anthracite are all produced from sedimentary rocks. And of course, most of our groundwater, particularly here in Florida, produced from groundwater bearing strata. Now in Florida, we have three main aquifers. North Florida has something called the Floridian aquifer. Floridian aquifer is composed largely of limestones, most prominent of which is called the Ocala limestone. Good news is it produces a lot of water, very clean, good water. Bad news is this is the strata that also creates the sinkholes, and then it dissolves rather easily, and then you have sinkholes forming. Part of the problem, the formation of sinkholes, is related to groundwater extraction, and the water table going up and down. That's just a scenario to create sinkholes. I'll talk about engineering geology a little bit in relation to some of the later stuff that we're going to see. This is probably one of the most famous oil wells of all time, called the Spindletop Well, built in 1901. The first oil well that actually produced any oil to speak of in the USA was the Drake Well in Pennsylvania, drilled in 1859. Drake Well produced oil at the huge depth of 60 feet, now 70 feet. And so the oil was seeping out into Oil Creek, and so they knew that something was going on there. And that produced oil from the Devonian rocks up in northern Pennsylvania. There was a group of entrepreneurs who looked around in Texas and said, hey, there's got to be some oil down here. Typically there are these funny little mounds that are created along the Gulf Coast. There might be some oil along these things. And so they drilled along one of them and created a spindle top well, which was a huge gusher. It gushed 100,000 barrels a day for a short period of time. And then produced a rather lot of oil, but over a very short period of time. It was also, by today's standards, very shallow. Only about 1,200 feet produced this tremendous volume of oil. The spindle top field later produced a lot of oil from deeper horizons, deeper depths. I'll show a picture of the structure of the spindle top field a little later. Note the drill rig that's, you see a few things like this still out in the Oklahoma, Texas area, but those are just derricks that are left standing. Most of the drilling is done by larger equipment, much larger. And of course, if you're offshore, you got yourself one of these puppies, which is an offshore drilling rig. This is the kind of thing that caused the tremendous explosion in the Gulf a few years back, 10 years ago, the BP oil spill. But they have all kinds of high technology equipment on these things, blowout preventers and things like that to prevent excessive oil leakage out of the
How far are they going down in the ocean, like the North Sea?
Well, it can go down as much as 20,000 feet. I think down in most of the wells in the Gulf of Mexico offshore platform, only go to 15,000.
Yeah, I was talking about off of the shore, like Norway or whatever. The North Sea.
Norway, I think they're a good bit shallow.
Shallow?
There are some shallow fields, a Groningen gas field off Netherlands that's really pretty shallow. But some of them are deeper, I'm sure. I don't know too much about that neck of the world, neck of the woods. Talking about oil and how it's produced and where it's produced, there are 4 main reservoir types that contain oil, and some are easier to find than others. This top one here called an anticlinal tract. An anticline is a structure where the rocks are bent upwards. They'll come down and then they'll come back up again somewhere else off in the distance. That downward bend is called a syncline. And it looks like kind of a sine wave, although they're nowhere near that regular. They're easily found because you can map the rocks along the surface and you can tell that when the oldest rocks are in the middle, that there's an anticline there. And most of the really huge oil fields in the Middle East are anticlinal fields. And there's one field, and I forget the name, that just produces huge amounts of oil for a long period of time. I mean, hundreds and hundreds of millions of barrels of oil have been produced from this one field. Another type of petroleum trap is a salt dome. And this is what spindle top was. The salt dome, and there was a little mound created by the salt coming up, and it was moving rapidly enough that it created a small surface depression. And these are fairly common in the Gulf Coast area. Spindle top was right by Beaumont, Texas. I happened to work for Texaco at a site that was only 40 or 50 miles from Beaumont. There's another salt dome called the Hackberry Dome, which was later mined so that they could put a lot of oil in it for the petroleum reserve. But the structure of the Hackberry Dome very much like this, and there are many other domes along the Gulf Coast like that, and there's a rather famous one called Avery Island. Anybody ever traveled around Louisiana much, this group? Well, Avery Island is a famous location, and they have salt mines there. They mine sulfur from the cap rock up the salt dome. These salt domes create movement up through the other strata. There's some dissolving of the salt that goes on from groundwater and water in the rocks. And it forms a cap, mainly of gypsum sulfate, the kind of stuff you make wallboard out of. Sometimes there's a lot of sulfur in this thing, and so that sometimes they're mined for that sulfur. Avery Island happens to be the headquarters of the McCormick Spice Company, the ones that make the Tabasco sauce. Tabasco is a good product of Louisiana. You see in these slides that there's usually water down below, there's a pool of oil, and there's natural gas above. That's the formation of the oil is created when these source rocks, which are usually shaly rocks with a lot of organics in them, are squeezed and heated, and eventually oily materials come out of it. The oils can be light, like what they call light sweet Texas crude, which is has a low sulfur and high amount of volatility, so you can make gasoline out of it rather easily. Some of the other oils, like the Venezuelan oil, is a very heavy, thick crude, very high tar content, kind of high sulfur, nasty stuff to refine, but of course there's a hell of a lot of it down there. Lake Maracaibo is basically a huge tarry deposit with a lot of water. Let me go back here. This is just a logic. Oh, I want to go back further. There are two other types of traps. One is a faulted trap. Faults are breaks in the rock along which the movement occurs. Earthquakes are usually occur along faults.
Yeah.
In California, most of the faults are what they call strike-slip faults. They move laterally to each other on the surface. However, along the continental margins and in other areas, some in the Rocky Mountains, and you get these faults which are one side goes up and the other side goes down. This fault plane usually is fused rock, and it creates an impermeable barrier. If there's a reservoir rock and a source rock, oil can be deposited and some gas. These are fairly hard to find unless you're in an area of active faulting where you can actually see the surface expression of the fault. The last and hardest to find are stratigraphic traps, where a strata will change from a sandstone to a siltstone to a shale, so reducing the permeability. And there's still a source rock that squeezes the oil into the sandstone, and a trap is formed. They're pretty tough to find, pretty tough to find. I just have a larger picture of the salt dome showing that. I don't know why I stuck this in, because the other one is a good picture too. Moving on to coal. This is how most coal is mined in the eastern half of the USA from the late 1800s, or actually earlier than that, to about 1970. And this is what they call room and pillar mining. They create these passageways up and down the coal seam, and they leave these pillars to support the roof. Otherwise, they couldn't get back to the working face. And they have, these days, they have coal cutting equipment, continuous miners. They have a machine that goes in and bolts the roof of the mine so that you don't get cave-ins. Sometimes you don't need a roof bolter. Sometimes the roof is competent enough that you don't need to do anything. Another kind of mining that's become more common because it's less labor intensive is what they call long haul mining, where this machine doesn't have a series of coal cars behind it, has a conveyor belt that goes across the face. This machine moves laterally across, and there are two tunnels at the edge of what they call a panel, and very efficient. This is the other major type of mining. The other, both two types are underground. This is a large strip mine in Montana. Montana mining a fairly thick coal seam. These coals are fairly recent relative to the coals in the eastern half of the USA, in that they are of Cretaceous age, whereas the ones in the eastern part of the country are mainly Pennsylvania. Here's a picture of the good old days. One miners mined coal by hand. There's a guy chopping out the upper seam, upper part of the seam. Here's a room going back in here. And another room started over there. This is in a bed called the Pittsburgh Coal Seam, and it was at one time deemed the most valuable mineral deposit in the world. Now I'm sure some of the Saudi oil fields could take that title. But this particular seam extends off there under all of northern West Virginia and eastern Ohio. And were very widely mined for many, many years, and it's still mined in some mines in Pennsylvania and West Virginia. This particular seam, much thicker than a normal coal seam. You see the guy standing up. I had a guy work for me who worked in some of the West Virginia mines, mining other seams, and the seam was only about 2.5 feet thick, and they laid on their stomachs on cars going back and forth and worked the mine. He told me a story about he had worked in the mine for a little while, and the Korean War occurred, and he volunteered, and he was at a range shooting his rifle at targets, and a general came along and looked at him and said, "This is pretty tough, isn't it, boy?" And he turned around and said, "You only been in a low coal mine in West Virginia. This is easy." The other kind of coal that we'll talk about a little bit more is anthracite coal. Anthracite coal is mined in the USA in 4 small basins in eastern Pennsylvania, and they are all tightly folded basins. This is the synclinal basin here at the Centralia location, and I think that's the middle coal field, western middle coal field. But you can see coal beds are steeply dipping here, and what they would mine at this particular location, they drove this long tunnel down through the rock, and they would mine the coal, and it would fall into the tunnel, and then it would be conveyed to the surface. Anthracite mining was very, very difficult to do, even in the later days, because of the dip of the coal seams and the added fact that they weren't very stable, very labor intensive, and so anthracite was expensive. But it was the premier fuel for most of the eastern USA in the late 19th century, early 20th century. And it's a fairly clean burning coal. It's not a gassy coal, so they didn't have a lot of mine explosions in the anthracite mines relative to the bituminous mines. One of the problems with coal mining is the effects on the surface. And if you're a homeowner in western Pennsylvania, eastern Ohio, all of West Virginia, you've got to be careful where you buy your home. And if you're prudent, you'll buy mine subsidence insurance, which is fairly inexpensive. But this kind of thing can happen. The coal pillars start to fail with time, and you get a crack in your house. This one is repairable. It's not pleasant, it costs, but it's repairable. Then there's something like this, where undoubtedly the coal mining was probably a little shallower at this location, and the cracks are huge. And you can see they've been repairing this building all along. I would expect that this one probably is the end of the line for this building, and they'll try it again. You can see the crack in the ground here from subsidence. Here's another example, small town somewhere or other. These individual holes represent the rooms in the coal mine. And you wonder why they built there. Maybe they built first and then they mined later. I'm not sure. I mentioned this town earlier. This is Centralia, Pennsylvania. Used to be houses all up and down the street. Now there's only a single house on the street. Reason why? Mine fires. It's a famous location for mine fires, been burning for many, many years. Thought that some fellow burnt some garbage in the strip mine on the outcrop of the coal, caught fire, went down dip, and started burning everywhere.
Is that eastern or western Pennsylvania?
It's eastern Pennsylvania, well, a little west of extreme eastern part. Basically north of Harrisburg.
Okay.
My firm did a study on this for the Pennsylvania Department of Environmental Resources. They were interested in finding a way to put out the fire, but it was way too expensive. It was way cheaper to buy up the homeowners and move them out to other locations where there wasn't any fire. This is pretty minor compared to this kind of thing. This is a coal field in India called the Jaria coal field. This is the main source of coking coal for the Indian steel industry. It's very important to Indian economy. The World Bank wanted a study done on this location because the Indian Coal Company wanted to borrow $500 million from the World Bank to buy new equipment to mine more efficiently. And the World Bank says, maybe, but we want to find out what's going on with the mine fires and whether they can be controlled. And so my firm did a study. It took a couple of years to complete. They had people living on site, not next to the mine, in town about 10 miles away. And we were studying this. Here is a picture of some of the residents, and they actually live in and around these fires. And they just walk through these fiery areas. It's a daily occurrence, no big deal. I was at a village, and there was a high wall there, and it was burning right next to the village, maybe 20 feet from houses. And just going about their business. And they didn't have to pay a lot to cook their food, they could just put on a spit and put it over the edge of the
Marshmallows.
Yeah, marshmallow time.
Wow.
Jeez. Doesn't even faze them.
Going on to things that are more on the engineering geological side, this shows a tunnel being drilled through sedimentary rock. This large circular thing here is a tunnel boring machine, and it's got a big back end where they are providing the power to all of these. See, these things here are individual bits that grind the rock away. And this big thing turns fairly slowly, maybe 10 RPM, something like that, and slowly grinds its way through the rock, and eventually you'll come through and meet the other end of the tunnel. Hopefully your surveys are good enough that you meet up exactly, otherwise you're going to have a rather embarrassing adjustment to make. But the underground engineering pretty good these days, so they don't have too many of these errors. If any of you have ridden the subways in Boston, you can see what's happened up in Boston, and that subway dates back, I think, to the 1890s. And it has some funny jogs as you're riding along the subway. That's because the tunnel surveys were off, and they had to make adjustments to make it work. Let me go back. Well, I'll show you this. What happens when you use the tunnel boring machines when the rocks are fairly hard and stable? Where the rocks are not stable, and you have cave-ins and things like that, they put in all of these reinforcements as they are tunneling. You can see they go up almost exactly to the face of the tunnel. And these are the machines that are drilling holes for blasting, to blast out another layer of material to keep moving the tunnel back forward. And you can see that there is sprayed concrete in here. This is a technique that the Austrians developed in some of their big tunnels that they drove through the Alps for vehicular and railroad tunnels. This is what a tunnel looks like. It's finished in the hard rock. You can see it's stable, it's standing by itself. There'll be a liner put in it, I'm sure, for whatever purpose that they're gonna put this thing to. And, so that's the tunneling in hard rock. And now, we get to the exam.
That was good.
That was good.
Very different.
What's the heaviest stone?